All right, it's 11:15. We'll get started. So any questions or comments? Okay, make sure to check out the homework. Sorry, I didn't post it until this morning. I forgot to do it this weekend. But homework number 8, download it, take a look at it so you know what we have to learn this week, and make plans to turn it in Friday, PLAs, all that stuff. So we've been talking about polymer characterization, and we've talked about a couple different ways to characterize the molecular weight. You have an N group analysis homework problem, I think, in homework number 8. But one of the standard techniques, and N group analysis is a robust technique when you have the conditions that allow you to do this. So identifiable N groups, enough N groups. You can either titrate them or you can use NMR to find the N groups. And so N group analysis works, but the real technique that most polymer labs use is size exclusion chromatography. So this technique is almost universal in all polymer science labs. And this is how we've learned a lot about molecular weights and molecular weight distributions of different polymers. So remember, the setup for size exclusion chromatography is that you put a mixture of molecules in a solvent. So these are dissolved polymers. And we want a good solvent. We want things, expanded coils, things that take up space. But we have a mixture of molecular weights because most polymers, how they're synthesized, give you polydispersity. You know, it's very rare that we have monodisperse samples. So monodispersity means there's only one molecular weight of a chain or one degree of polymerization. And so you can get dispersities of 1.02. 1.04. Does anyone know what synthetic technique is usually used to make nearly monodispersed polymer samples? We've studied it. And so you need a very well-controlled polymerization. You need something that's predictable. You need something that probably doesn't have a lot of termination or chain transfer. Does anyone remember what type of polymerization that is? Living, and especially living anionic. So living polymerization gives you a predictable increase in molecular weight as a function of time. It's linear, so you can really target certain molecular weights. And because anionic polymerization doesn't have any termination or chain transfer, typically, there's not a lot of things to go wrong in that living process. And so we talked last time about standards or monodispersed standards that are used to calibrate the size exclusion chromatogram in terms of molecular weight versus retention volume. And those are usually made using anionic living polymerization. Sometimes they use cationic ring opening if you want like a polyethylene oxide standard or something unique. But you know, in order to calibrate the GPC, you need some monodispersed standard. Sometimes they do N group analysis to get a different type of calibration for the molecular weight, but that's how those standards are made. But most things like free radical polymerization, step growth polymerization, all the other stuff we studied, you'll have dispersity in molecular weight. Okay, and what the chromatography column does is it just separates things by size. That's why we call it size exclusion. And remember, we're trying to connect the size of the molecule to the molecular weight. And we have some models for that, right? The end-to-end distance, really size exclusion chromatography is hydrodynamic volume. But we have a sense that polymers with higher molecular weight form bigger coils or particles, as we call it in these notes, in solution. And so we separate by size, which is a proxy for molecular weight. And then the key part of this is the detector tells us when polymer is coming out. So the detector is usually refractive index. So this could be refractive index or viscosity. It turns out that these are very sensitive measurements for when there's a little bit of solute or a little bit of polymer in solution. There are other types of detectors as well, but these are the big ones. And so all this detector is doing is saying there's polymer here, there's polymer here, there's a lot of polymer here. It's giving you the response, this amount of polymer, which is the detector response, as a function of elution volume. So the detector doesn't know what the molecular weight is, doesn't know the size, it doesn't know anything. It's really connecting the elution volume through the chromatography column to the calibrated monodispersed molecular weight standards. And then the amount of polymer or the detector response is just saying there's no polymer in this solvent as it's coming through the column, because remember, you're flowing solvent through the column steadily as a function of time. There's a little bit of polymer here because the detector signal goes up. There's a lot here, then it goes back down. So you want to have a sense for how this instrument is put together in the physical processes that are happening. And the key is you have to think about the size. If you're not thinking about the size of the molecules in solution, you don't have a very good idea of what's happening in terms of how the molecules go through the chromatography column. And the tricky part of this is that large stuff goes right through the column. So large particles or high molecular weight polymers come out first at low elution volume, and small particles get stuck in the pores of the column and they come out later. So it, in some sense, is backwards from what you might think. So fast stuff travels more quickly through the column. All right. So what we do, well, let's back up to the calibration slide. So this is just amount of polymer versus elution volume. So that's the raw data off the instrument. Detector response versus elution volume, and you're measuring the flow rate, so you can figure that out. And these standards have no NM. They're usually made by anionic living polymerization. And in lots of cases, they're polystyrene. In the solvent of choice for the unknown polymer. So even if you're not making polystyrene as your unknown, usually you calibrate the SEC, or the size exclusion chromatography instrument, using dichloromethane or using toluene or using chloroform or whatever solvent is appropriate for your unknown and polystyrene. Because we know that as you change solvents, and of course, as you change the polymer chemistry too, the solubility parameters are changing. So that coil can contract and expand a little bit depending on the polymer solvent match. And that's the really tricky part about SEC, is it's hard to get a perfect calibration because the polymer solubility parameter is always moving around a little bit, and the solvent has different solvation quantity or qualities for the different polymers. So that's a pitfall of SEC. But once we can calibrate our known molecular weights versus elution volume, so you get some sort of calibration curve like this, now we can construct the or the weight average distribution of our sample. And so we're looking at weight fraction versus molar mass. So this is an indication of dispersity. And so if you go back to the molecular weight slides, when we talked about MN, MW, and dispersity, we looked at number fraction and weight fraction as a function of molar mass. And we were able to talk about what that distribution was, the first moment, second moment, dispersity, etc. So this is how we get one of those curves in the first place. And so what we do is this amount of polymer is relative, and so we have to normalize the area under the curve to 1. Why do we normalize the weight fraction to 1, or the area under this curve? Anyone know why we do that? Mole fractions and weight fractions have to add up to what? 1, right? So we don't know, we don't have like grams of polymer here, and so we have to normalize this curve. This represents all the different masses of the different molecular weights, and all those masses, their weight fractions will have to add up to 1. So it's not just a mathematical trick. We know that mole fractions and weight fractions have to add up to 1. And then what we do is, once we slice this curve up into small sections, that is a weight fraction. And it's a weight fraction with a certain molecular weight. So if the entire area under the curve is the total weight fraction, or the sum of all weight fractions, right? That one slice of area, I know you remember this from calculus, is the weight fraction for a given molecular weight. Because we can connect VE, we can calibrate this to molecular weight, right? Like that. Okay, so even though it looks like we go from a Gaussian curve right here to something that's not quite Gaussian right here, that's fine. The peak shapes will shift around a little bit. We don't even have something that's perfectly Gaussian here, because we probably don't have a Gaussian or a bell-shaped molecular weight distribution in the first place. But this is just illustrating the point where you can go from experimental or machine parameters that are measured by the instrument to our molar mass distribution. And you notice that if we sum up the weight fractions times their molecular weight, we get the weight average molecular weight distribution. Does anyone have any questions or thoughts on that, or things they want to ask about? So this is tricky because it takes a number of things to understand what's going on. Of course, I'm not going to ask you a question on the exam to explain the whole thing, but I might ask you, how is the calibration done to calibrate the elution volume and the molecular weight? You'll say, well, I have to measure the elution of monodispersed standards to make sure I know what molecular weights are coming out in what elution volume, right? Or I might ask you about what type of detectors are used in size exclusion chromatography. And so you could tell me about that. So you want to take a peek at these slides and try and understand step by step how this process works, and ask questions about it in the next couple of weeks. All right. So this is not a clicker question. We did this last time. But the way to think about what these curves mean is we often have two different curves that we're comparing. So we've got log molecular weight. This is usually just plotted on a log scale to make the plots a little bit more linear. We've got elution volume here, or sometimes it's retention time, because if we know what the flow rate is, we also know what the time is as well. And if we compare two curves, we can talk about which polymer is larger in solution versus which polymer is smaller in solution. So given curve 1 and curve 2 here, which one is larger in solution on a relative basis? So at a given molecular weight, this is not a clicker question, you don't have to worry about that. For a given molecular weight, which polymer is larger in solution? Go ahead.
1.
Yes, 1 is larger in solution, and we can read that right off the plot. Why is 1 larger? How do we know? Go ahead.
Oh, okay. Because it takes less volume to get the same molar mass.
Yep, 1. So at a given molar mass, M, polymer 1 has a lower solution volume than polymer 2. So that says polymer 1 is larger in solution. So right away, you have to draw on your knowledge that things with the lower elution volume are bigger in solution. And it could be bigger for a number of reasons. It could be different polymer solvent combination, right? It could be more solvated compared to polymer 2 that's going to have a more collapsed coil or has a larger difference between the solubility parameters. Or in this case, we talked about branch polymers versus linear polymers. And the trick to this question is knowing that branched polymers for a given molecular weight are smaller than linear polymers. And we can sort of get that because of these junctions. There's more repeat units of the polymer in a smaller space when you have branching. Does everyone understand that? Is everyone sort of thinking about this? Because these are the types of questions I'll ask you. What's smaller? What's larger in solution? Why? What does the SEC data look like? Things like that. Questions or comments? All right. Great. So that's your 10-minute review of size exclusion chromatography. And we do that because this is such an important technique. This is also called GPC, which is gel permeation chromatography. So whether you call it size exclusion chromatography, which a lot of people do, or gel permeation chromatography, it's exactly the same thing. And they call it gel permeation chromatography because the column is usually some cross-linked gel. It could be silica that's cross-linked in there. Sometimes it's polystyrene, like a polystyrene mesh that's cross-linked. And so it's a gel that's sitting inside this column. And so you see GPC, but they're exactly the same technique. So we can use SEC because it's used for a wide range of polymers as long as they're soluble. If you have a polymer that's insoluble, don't put it in the chromatography column because they'll just sit in there forever and you won't get anything. We can even do aqueous size exclusion chromatography for water-soluble polymers. And what's so powerful about this is we can get the distribution of molar mass and the dispersity. Let's not put PDI there, let's put dispersity. Polydispersity index is an old term for dispersity, but polydispersity is like you're saying the same thing twice, right? There's lots of dispersity, you know, that's what dispersity means. Okay, so this is important because N-group analysis, when you go through the math on your homework, you don't get the molar mass distribution from N-group analysis, right? You just get one number that's average. So that's something to think about. Limitations. We're equating hydrodynamic volume to molar mass. That's not always perfect, especially if we're trying to compare branch versus linear polymers. And there's issues with solvent quality and interaction of the polymer with column, etc. So these are just things to think about. And every time we talk about a characterization measurement, you do want to think about the pros and cons, right? What works, What doesn't group? What doesn't work? N group analysis works if the N groups are identifiable. You can do titration, atomic analysis, things like that. N group analysis doesn't work when there aren't lots of N groups or you can't see them in the polymer. And so everything will have a pro and con, and that's something to think about. Questions or comments? All right. No hands? All right. So we're going to move on to thermal analysis of polymers. And so when we talk about thermal analysis of polymers, what are we really trying to measure? What are some important thermal properties of polymers that we really want to get a handle on? Yeah.
Elasticity.
That's not a thermal property. That's a mechanical property. Yeah. Yes. TG. What else? Maybe thermal conductivity. That's a good one. What else? Yeah. Tensile's mechanical property. You can measure elasticity and tensile as a function of temperature, but you're measuring a mechanical response. In these properties, we're measuring the thermal response. So what other thermal properties of polymers do we care about? Yes. TM. That's a good one. What else? Yes. Thermal expansion. Coefficient. Or the CTE. What else? There's another really important one that sort of goes along with, I'm heating up a polymer, I go through the TG, I heat it up a little bit more. If it's a semicrystalline polymer, I go through the TM. What's sort of the last temperature of the polymer where things happen as I keep heating it up beyond the TM? Yeah.
I don't know the term, but it's like degradation.
Yeah, it's actually called TD, which is the degradation temperature. So right on. So this is degradation temperature. So, and you really want to know the degradation temperature because that tells you ultimately, okay, let's not bring our polymer up above this temperature or else we're not going to have the same thing that we had when we started. Like when we cross TG, it's the same exact polymer, assuming there's no side reactions or weird stuff happening. It's the same polymer above and below TG, just in a different physical state. Same with TM. It's a polymer melt above TM, or it's a crystallized polymer if it's a semi-crystalline polymer below TM, but it's a phase transition. So you don't have any chemical reactions. The degradation temperature of the polymer is when the organic bonds or the covalent bonds of the polymer start falling apart and you can't get those back. You're doing chemistry to degrade the polymer. What's a sort of relative temperature when we think about the degradation of polymers? What sort of a temperature to think about in terms of most polymers don't live above this temperature? Does anyone have any ideas? C, so boiling water. Do we use polymers in boiling water? Yeah, we do. So 100 C is where TG and TM live. You know, there's a good span of those, and we'll talk about the temperature span for TG and TM. But what about degradation? Yes.
I'm gonna guess between 300 and 500 C.
Yeah, so getting up to like 400 C, 500 C, definitely. There are very, very few polymers that survive above 500 or 600 degrees Celsius. And in oxygen, it's even worse because you know that 451 degrees Fahrenheit is when cellulose burns in air. Cellulose is a good polymer, right? And so I don't know what 451 Fahrenheit is in Celsius, but really we're talking most polymers are used up to about 250 degrees Celsius, and that's it. So the degradation temperatures, they're just way too soft. Degradation temperatures, 300, 350 degrees Celsius, 400 degrees Celsius are where most polymers are used. And that's why we don't make fireplaces out of polymers, right? That's why we use masonry brick and ceramics or metals for high temperature reactors. And so polymers are really, really useful for all sorts of consumer products, but they're less good at high temperature resistance than some of the other available materials. So that's something to think about in terms of what's the ballpark. All right. So we go back to our Gibbs free energy, because that's always a good place to start when we're changing temperature. And so why do things crystallize? So when we go from liquid water and we cool liquid water down below 0 degrees Celsius and nucleate it, we get ice. Why does that happen?
Because it is crystalline.
Yes, because it's thermodynamically favorable for the ice to crystallize at that low temperature. Otherwise, it would not happen. We just talked about the sign of delta G, right? So as you lower the temperature of liquid water, the delta G is going from positive down, 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 0, right when we're at the equilibrium temperature. And then eventually the delta G is negative. And so there's a driving force for water to crystallize at lower temperature. And the same thing is true for polymers. And that driving force is delta H. What do we call that delta H number, that driving force for crystallization? It's called by something else usually, but what's that property? The heat of what? Chemical engineers, you should just know this, like, ding, right off the top of your head.
There's so many.
And the enthalpy of what, or the heat of what, for at a phase change is called
Reaction.
no. There's no chemical reaction there.
This is from a liquid solid liquid, right?
That's right. Heat of fusion. That's right. Someone said heat of vaporization. That's going from liquid to gas, right? But it's a phase transition, just like this is from liquid to a crystal. But it's the heat of fusion or the heat of crystallization is the driving force for this process. And we know that because every single substance that crystallizes gives off heat when it crystallizes, right? And you have to, it's always exothermic. And every single crystal that you melt is endothermic. It has you have to overcome the heat of fusion, right, in order to melt that crystal. And that delta H is the driving force because the crystal is lower entropy. And nature does not really want to go to lower entropy states unless something is given back. And that something is the heat of crystallization, right? So crystals just don't form spontaneously. I mean, you don't, if you have a water bottle or something sitting there at room temperature, crystals won't form spontaneously because those water molecules really don't want to be locked into a low entropy state. And a crystal has lower entropy than a liquid, right? The configurations are less. And so the only thing that can drive crystallization is this heat of fusion. And that's really interesting if you think about the free energy as a function of temperature. And you can map this out for crystals and melts. At low temperatures, you're going to have crystals because they are lower in free energy. And the system always wants to seek the lowest free energy state. And at higher temperature, melt is the lowest free energy, or liquid. Just put liquid. And so that's the lowest free energy. And so that's going to be more thermodynamically favorable. What's this crossover temperature called right here? What's that temperature? TM. And it's the TM because when you go from a crystal to a liquid, that's a formal first order phase transition. It's defined as the TM. And we'll talk about what a first order phase transition means versus a second order phase transition. So this is just, let me move this guy. This is just a refresher on crystallization, because I think you've seen this before in various places, but this is really important to remember because it's different than the glass transition temperature. And so we're going to talk about that, but you really want to remember that delta H fusion or delta H melting, whichever one, they're exactly the same process, right? It's just the other direction, is a first order phase transition. Great. And we'll just put delta H fusion there in parentheses. Okay. We've seen this before. What's TG? What's TM? And so one thing to remember is that all polymers have a TG. And we can measure TG in most polymers. Sometimes the glass transition temperature is higher than the degradation temperature if you have a really strongly hydrogen bonded system. So it's really hard to measure the TG of Kevlar because it degrades before you get to the TG because it's so rigid. But theoretically, all polymers have a glass transition temperature because they're macromolecules. Some polymers have TM. What's the requirement for the polymer to have a TM? TM is the crystal to liquid melting temperature, right? So when that semi-crystalline polymer melts, what's the requirement for a polymer to have a TM in the first place? Yes?
Linear?
Nope. More general than that even. Nope. It has to be a semi-crystalline polymer in the first place. So not all polymers crystallize. So you need to know if it's a semi-crystalline polymer or always amorphous. And there's a lot of really cool examples of this. So polystyrene is always amorphous. You cannot get atactic polystyrene made using free radical polymerization to crystallize no matter what you do. Isotactic polystyrene, did I just say atactic polypropylene or did I say polystyrene?
Atactic polystyrene.
Okay, atactic polystyrene is always amorphous. Okay, that's good. Isotactic polystyrene made using coordination chemistry is semi-crystalline. So you can take the same molecule, you can make it a different way, you can add in tacticity, and then it will crystallize because it's a much more regular structure. And crystals love regular structures, or regular structures love crystals. Polypropylene, when you make that using Ziegler nanopolymerization or coordination catalyst, isotactic polypropylene is a great crystallizer. But if you make it atactic polypropylene using high pressure free radical polymerization, it's amorphous. So when you lose the tacticity, you get amorphous polymer. High density polyethylene, HDPE, is mostly linear. You can't do a lot with isotactic or atactic polyethylene. It's not defined because it's not a chiral polymer. High density polyethylene crystallizes great. If you make branched polyethylene, which is called low density polyethylene, or linear low density polyethylene, it crystallizes to a much lower extent because branches don't allow crystallization. So you don't need to know all of that for this class, but having some idea of examples of when does a polymer have a TM, and some polymers that do like to crystallize, like polyethylene and isotactic polypropylene, are really important. And then knowing a couple polymers like polymethylmethacrylate or polystyrene that don't crystallize are really important. There's a really cool example of this. It's polyethylene terephthalate. Does anyone know where we use PET a lot? Yeah, in water bottles. Is polyethylene terephthalate a semicrystalline polymer or an amorphous polymer? You might guess amorphous because why? You look at a water bottle and what is that polymer? It's clear. And a lot of things that don't crystallize are clear because when you grow crystals, crystals have a different refractive index than the same thing when it's amorphous, and large enough crystals scatter light. So that's why window glass, we use amorphous silica rather than some sort of crystalline silica, A, because it's cheaper, and B, we don't have any cloudy windows. But polyethylene terephthalate has really, really small crystals. It's clear, the crystals are very small, and the crystals stop oxygen from permeating through PET. That's why it's a good material for carbonated beverages, water, all of that sort of stuff. So looking at the polymer is one indication, but PET is the counterexample where the crystals are just really small, you can't see it. So you'll learn more stuff like that as we go on, but it's really useful, like I said, to have an idea of what's happening with semicrystalline polymers and amorphous polymers. All right, now this is a really important slide. TG, glass transition, formally defined, versus TM, which we just talked about. There's definition for TM and TG, and they're different. So crystallization and melting is TM. First order phase transition, you go from amorphous melt to a crystal, you have a delta H fusion, all that stuff. Why do we call polymers semi-crystalline? I mean, once in a while I'll call them crystalline, but why is semi-crystalline the thing used for polymers? Well, it's part, not exactly half. We don't have to use half, but we always have, you notice here, always have some amorphous polymer, even in a highly semicrystalline system. So even like high density polyethylene, the most regular chain we can think of, when we crystallize HDPE, it's usually only about 70 or 80% on a volume basis crystalline, and then the rest is amorphous, because the polymer has to be amorphous, where there's liquid-like order or no order if you want, or semi-crystalline, there's nothing in between. And so even the polymers that crystallize the most are not 100% crystalline. And that's completely different than metals, than a lot of small molecule organics, right? There's no amorphous fraction of ice in your ice cube. It is all crystal. Same thing with metals, although you can make some of these things amorphous, or you can make them glasses if you process them in a special way. But most things that form crystals are either all crystalline or polycrystalline, lots of crystals with grain boundaries, or they're liquids. Polymers are in this intermediate regime. Okay. When we're at high temperature or above both TG and TM, polymers are viscoelastic liquids, or they're melts. We call this a polymer melt. And let's take the easy case where we have a completely amorphous polymer that will never crystallize. as we cool it down, we go through a glass transition temperature, and you notice that this amorphous melt, which is a liquid, has liquid-like order, sometimes we call it that, no long-range regular order, looks nearly the same as this glass, right? No order in a glass. That's a really interesting physics problem. It's completely amorphous, but it's solid. So below the TG, you have no translational diffusion of molecules. They are frozen in place. They are not crystallized because they're not in a crystal, but they're frozen in place because the temperature is so low they don't have any thermal diffusion. That's the only difference between the order or this melt where the chains can slide past one another, right? The liquid can flow, and in a glass, the chains can't slide past one another, at least on any sort of reasonable time scale. And so that's defined by this glass transition TG. Now, can a polymer have both a TG and a TM? Yeah, no problem, right? All polymers have a TG, so we're set there. Some polymers have a TM, and so some polymers, any polymer that has a TM has both a TG and a TM. And it's interesting, you can probe those differently. So in the melt, when you're at high enough temperature, there's no crystals, there's no nothing. You cool that polymer down, and first it will crystallize, right? So you go from a melt to a semi-crystalline polymer where the amorphous fraction is still in the melt. And then eventually you go through the glass transition temperatures, you decrease the temperature further, then that amorphous fraction becomes frozen. Because you can't crystallize from a glass, right? If there's no translational diffusion of those chains, you can't make a crystal because they can't move around. And we'll talk about the order of TG, TM, et cetera, as we go on, but that's a really important point. Questions or comments? All right, there is a whole class on this in your upper division, or at least part of half of a class if you're really interested in crystallization, thermal properties of polymers. Yeah, there's some really cool stuff in the 400 level polymer classes. All right. So we'll start off with some sort of qualitative observations, is that if we make polymers out of different repeat units, so different chemistry, we can sort of get a qualitative idea of what the TG is going to be. And this is basically born out of experience. And so you think about the properties of these different functional units. So whether it's something that looks like polyethylene, something that looks like polyethylene oxide, right? PEO, and some aromatic polymers. And then we have all of our vinyl polymers here, where X is our substituent unit. And so we know that the TG really describes the mobility of the polymer chain, right? If the polymer is frozen, it's glassy. If the polymer can move around, if it's nice and flexible, it's a liquid. And so stiffer polymers or polymers with less flexibility have higher glass transition temperatures. Polymers that are super duper flexible and can move around easily have lower glass transition temperatures. So you notice that polyethylene has a very flexible backbone because there's no rotational barriers around that carbon-carbon single bond, right? So the TG of polyethylene is minus 130 to minus 10. It's hard to measure because it crystallizes so fast. But why do we use polyethylene in milk jugs and packaging and other stuff if it has such a low TG? The TG of minus 10 means it's a liquid at room temperature. So why do we use it? Because it crystallizes and all those crystals lock polyethylene in place. So it feels hard because of the crystals at room temperature. But the amorphous fraction of polyethylene is still liquid at room temperature. That's why it's got really high permeability. That's why we don't use polyethylene in water bottles, but still, that's a really interesting fact. Polyethylene oxide, you know that ethers are very flexible. So PEO is a nice flexible polymer, has a low glass transition temperature, which means it's a liquid at cold temperatures, right? It's a liquid at -20 C, it's a liquid at -40 C, and then it doesn't become a glassy solid until the temperature is below -67 degrees Celsius. Okay. Benzene rings or aromatic rings make polymers more stiff. So polyparaxylene, which is basically like polyethylene or polyethylene oxide with an aromatic ring stuck in there, has a glass transition temperature of 80 degrees Celsius. So TG of 80 means you have to go above 80 to make it a melt, and below 80, it's a glassy solid. It's, you know, a glassy solid like this is. All right, and for vinyl polymers, there's a really nice progression where bulky things have high TG, polar things, like this nitrile here, has high TG. And so you can think about the chain flexibility and steric interactions and the intermolecular interactions, and that gives you a relative scale for TG. And you notice most of these temperatures, I mean, there's some low ones there, but -100 degrees Celsius to 100 degrees Celsius is good for garden variety polymers, although some polymers have TGs of 200 degrees Celsius, 250 degrees Celsius in high performance polymers. So this is worth thinking about what these bulky substituents or what more flexible substituents might do to the glass transition temperature polymer. Any questions or comments on this? Okay, we'll keep going. We have a few minutes. So how can we characterize TG or TM? And the best thing to do is think about volume, and that's really interesting. And there's just one or two more slides here. Covered a lot of theoretical ground today. Okay, so free volume is a concept of empty space between molecules. You can't put anything into the free volume. It just exists because you can't get the orbitals perfectly locked into each other in any sort of system. So free volume is extra space, doesn't fill up with anything. It's not full of air, it's not full of water, it's just there. When you take a crystal and you melt it, you increase free volume. And the extra free volume in this liquid is actually what allows the molecules to move past one another, right? There's not enough space for molecules to move past one another in this crystal. They sit there. Once a molecule is in a crystal, it is in its same position for a really long time. But liquids, the molecules change places, and that's because of free volume. Now, dilatometry is the study of volume as a function of temperature. And so the one thing that you need to remember in this section, and this is the last slide we'll cover, is that a crystal has a discontinuity in the volume versus temperature curve. That's why it's a first order phase transition. And it has a defined delta H of fusion. So you need both of those things. That's what defines a first order. If you look at this TG, it doesn't have a step change. It has a change in slope. And there is no delta H for the TG. That's why it's second order. So there's no like delta H TG or any glass, heat of glass formation. There's nothing like that. And so TG is second order phase transition. And we can see that right from the melt at high temperature to the glass or crystal at low temperature. And we're going to talk about this plot in detail on Wednesday. See you then.